time. So one of the issues with computing in today's age is that in order to go faster, you have to break down time into smaller increments. But that's difficult for modern computers. So here we have a quantum computer. So it looks like more is going on than actually it is. So really they're just using these different materials that can go to low temperatures. China has systems where you can see the crystals, but also you can see the different mirror setup as well. So a qubit it simulates an atom. So when you're using a quantum computing, basically you're computing and simulating the natural dynamics of the universe.
There would be, as things become much faster, people and countries are going to be spending a lot on quantum computers, because I believe you can break passwords as well when your system is so...
With an atom, you can build anything with an atom. So
it's a building block. It's a building block.
Yep, but with a bit, you can't build anything with the bit.
This has been a very, very interesting conversation with Ian. We discussed quantum, and it's going to be the most important technology for the whole world. We discussed how countries that are going into quantum would have a huge leverage over the countries which are not. And we discussed how quantum computers work, and we discussed lots of applications, and Ian showed some of his work in quantum. It's so important, and this has been an amazing conversation. We really, really thank Ian for all the work that he shared and all the work that he has done. Enjoy the conversation.
Hi Ian, welcome to the talks, and I believe this is going to be very interesting. Looking forward to be working on that. I'm also myself interested, so it's a common space that we have. We can possibly start with, about yourself, and then we can move into quantum computing. This is going to be highly interesting.
Absolutely. So my background originally started out with law, right? I came out of law school in about 2011. I worked in the community for about a year. While I was doing that community work, I was working more so on the workforce development side. And I wanted to answer the question, how we can best prepare a future workforce. Soft skills were being heavily pushed at that particular point in time, but you can have all the soft skills and be the nicest person in the world, but not have the actual technical skills needed to actually fulfill the role. And so we got into hardware and technology in about 2014. And we were introducing the technology in impoverished areas in the community, such as drone technology. We were working with blockchain technology back then as well, and AI. During that research, we realized that there were limitations. There were hardware limitations that we kept running up against to do certain things that we wanted to do. And also there were other limitations as far as software, right? And so just the whole hardware software stack for developing automated and autonomous applications, there were some barriers to bandwidth and performance that we needed in order to run real-time applications on things like a drone or a self-driving car, etc. So we started doing research in the quantum field in about 2016. And at that point, we knew that in order to extend our AI applications in particular, and to be able to run more real-time applications, that we were going to have to go in the direction of quantum technology. Back then, our organization didn't have the technical expertise to be able to deploy that. And we've had to gain that expertise over the years to get to the point where today we can deploy commercial ready quantum applications.
Amazing. From law to quantum. It's a very different gap, but that's how life turns to be. So, on this podcast, there are many people who may not know what a quantum computer is, or they may know it faintly. So what's a quantum computer in simple terms?
Yes, the best way is to is to allow me to give you an analogy, right? So we'll talk about classical computers being the computers that you're probably watching this podcast on versus a quantum computer, which there may be about, at least in the United States, IBM might have about 60 of them, right? 60 plus. And so there's not that many of them. And so the biggest difference would be, imagine a classical computer being a flat piece of paper, right? On each side of that paper, right, you have an option, just like flipping heads and tails, right? So you can have a 0 on one side or you can have a 1 on the other side. But quantum is more like a ball, like a round ball, right? And if I asked you how many sides does this ball have, you would say like infinite sides, right? Because it's a ball, right?
Yeah.
And so that's the difference in computing as far as capabilities are concerned. The possibilities are limited with classical computing because you only have a 0 and a 1, right? The two sides. But with quantum computing, because you have infinite possibilities and infinite sides, right? Or infinite ways that a problem could be solved, there's way more that you can do with quantum computing from that particular perspective. So we'll just talk about the complexity, right? If you had a two-sided coin or a two-sided piece of paper, right, there's with that concept, there's certain limitations, right, as far as what you could do with only 2 dimensions. But if you have an infinite number of dimensions, there's infinite possibilities as far as what applications you could create. So developers often find that they'll run up against hardware limitations as far as a concept that may be too memory intensive for them to run on a particular computer. Or they may have, for example, some application that needs enhanced security because hospitals and government agencies have been getting hacked like crazy. And so that's where you would make that transition beyond computing. But the issue is, for your average consumer of technology, is that they've only experienced the technology in the 2 dimensions. So they have no idea, because they haven't worked with quantum. They don't understand that quantum can take their problems that they're working on and solve them in new ways that they've never thought of before.
Great. So what I heard about is that quantum computer is about 150 million times faster than the supercomputer, the fastest supercomputer right now. Is that true? Is it that fast?
Yes, and it gets faster the more qubits, or and qubits could essentially replace the bits in a classical computer. But the qubits serve as that
What's
circle, right?
What's qubit actually?
So a qubit it simulates an atom. So when you're using a quantum computing, basically you're computing and simulating the natural dynamics of the universe, right? And so instead of computing in a analog way, right, where you're using the zeros and the ones, you're going beyond digital, and you're essentially mimicking the optimizations in the universe, right? Because the universe is already optimized. So think about it. With an atom, you can build anything with an atom, right? You can build anything with an atom. So
it's a building block. It's a building block.
Yep,
so we can do
Yep. But with a bit, you can't build anything with the bit, right? It's limited. And so it forces us as developers and programmers and creators to completely break how we think about computing and what the possibilities are, different programs or applications that we can create. There's different ways that we can show and simulate and express the technology that goes into our applications, for example. So you may simulate a process that or an algorithm, right? But normally when you create an application, your customer doesn't get to peek behind and see that algorithm, right? So that's actually perfect for artificial intelligence, where there's a huge issue with the lack of transparency with AI models and algorithms. But with a quantum application that a hybrid, for example, that you simulate on a device, you can actually show the user the processes that take place and simulate those processes so that the user gains more insight into the inner workings of that artificial intelligence model and how it comes to its conclusions and its results.
I want to go back a bit. Bits are zeros and ones. So, for like normal reference, and we cannot, as you mentioned, that we cannot replicate that much. But qubit is another layer over a bit. Qubit is another layer over bit, right? So, what does qubit enables us? And are quantum computers having a speed in qubits? Because I saw that there are a few quantum computers who are like 5 qubits, seven qubits. They're like small, and it goes. I believe that China and IBM have very large qubit models. So, what are their speeds? And let's start by what exactly is a qubit.
So a qubit is just like we talked about, a building block in a method to conduct computation. And essentially the reason why a qubit is so much faster than a bit is because a bit can only process information in 2 dimensions, and a qubit can process information in infinite dimensions. And the best way to discuss this is to think about a path planning problem for a robot. So suppose you have a warehouse robot that wants to get from one side of the warehouse to the other side. And what normally robotics would have that robot do is it would go down each of the aisles and essentially all aspects of the maze until it actually finds the exit point, right, or the endpoint. But with quantum, what it would do is quantum would allow it to analyze all options at once, right? Mm-hmm. And so as a result, the amount of efficiency from energy savings, the amount of processing, that power that is saved is immense. And so that's why you have it where qubits are much more powerful methods of computation or tools of computation than utilizing your bits. But to get to the point of the differentiation between the large numbers of bits, IBM recently, I think yesterday, they just came out with their new quantum computer that has, I think it might have like 1,000, little over 1,000 qubits. Our organization has created simulated quantum computers that we've simulated between 1 million qubits and 1 billion qubits. But we've had to utilize models, computational models that are inspired by nature and are biologically inspired, so to say. And so by becoming more in tune and more in line with nature, we've been able to gain computational efficiencies and optimizations and improvements that we wouldn't been able to have gained had we used normal computation. And so, for example, right now with AI, quantum computing is the most impactful we see in the AI field. And that's primarily because AI is so energy intensive and computationally intensive. And so what you have to do is quantum almost tricks your computer into thinking that it has these powers that it doesn't or shouldn't naturally have, right? Through things like simulation and hybrid quantum computing. And so essentially what we're doing is we're taking the capabilities of existing computing and we're extending them using a hybrid quantum setup and essentially meeting the standards in that day when our full quantum, not hybrid, full quantum computing comes into ubiquitous existence. And so quantum computers exist now. They're just not ubiquitous because of normally the way that they stabilize qubits in order to make them computationally useful is they freeze these systems and these machines to sub-zero temperatures in order to be able to control and slow down the natural biological processes, right? Or the quantum processes. And so as a result, there's a lot of technology behind it that I feel like is almost irrelevant to a certain extent. Because, for example, think about the internet, right? Everyone can't really tell you how the internet works. They don't know about the IP protocols and, all those other aspects of it, but it does have utility. It does work better than the radio, for example. And so I would compare the type of experience and the user interface and the interactivity that one could have on the internet, comparing that to radio when individuals were just interacting from that perspective, or even the TV, because the TV really isn't an interactive medium, right? Quantum provides you that leap from the radio to the internet, or from white and black TV to the internet, and it allows different experiences, customer experiences, different processes to be much more rich and much more granular and detailed. Another example that I'll give you that I feel like will help is time. So one of the issues with computing in today's age is that in order to go faster, you have to break down time into smaller increments. But that's difficult for modern computers, right? Like modern computers start to break down at the microsecond level. And so as a result, quantum capabilities can give you that granularity where you can break down time into smaller increments beyond what currently you could do on a classical computer. And so for AI, for real-time systems, where you have a car that needs to stop when it sees a pedestrian, right? That microsecond is the difference between a person's life or a person, not being here on this planet. And so, medical technologies where the diagnosis has to be correct, right? It has to be sensitive enough to ensure that it's giving the correct answer. And so that's why you see quantum already in society in areas like GPS systems, right? Quantum's already in GPS. Quantum is already in laser. Yeah, it's already in GPS. It's already in lasers. It's already in MRI machines for scanning for things like cancers and tumors, because it has to be sensitive. And so most people just don't know that it's being utilized, is just not ubiquitous because the technology has not been accessible.
Right. I want to circle back to a few things. It's amazing. What you're saying is highly interesting. So you mentioned that IBM, when I read, it was what I read that the Zhongqi is like China's computer, which they mentioned is the fastest. Is it not right now?
Yes. No, China. It's because they have a quantum computer that's based on a mirror system, right? Where they're bouncing light around and they're utilizing photons instead of simulating atoms, right? And so the different types of quantum systems, really different countries are playing with different types of setups and hoping that one of these will gain an advantage over the other. So that's why you see so much money being thrown into the field of quantum computing, and it really being at a discovery stage and being where the AI field was about a decade ago.
Right. And then it was like IBM's Osprey computer, which is about 127 qubit Eagle. But now you are saying IBM came out with 1,000 qubit system yesterday, right?
Yes.
1,000 qubit. That's amazing. And you mentioned that, you can, some of the systems that you have developed are like much more than 1,000 qubit. How does that work? What kind of systems you have derived? How does that work?
So we actually had to completely go away from IBM to create these systems that have many more qubits, which made me realize that Qiskit, which is the IBM library for building quantum applications, more than likely has a governor on it that limits. For example, using Qiskit, the highest that you can go is utilizing 24 qubits, right, with the open source technology. And so because of that limitation, there were problems that we couldn't computationally solve, or it took too long and it ruined the consumer experience. So for example, suppose that I have an application that's supposed to load and it's quantum. If it has a smaller amount of qubits, then it's going to take longer to process, and that may be too long. The consumer's not going to wait 2 minutes, right, for your application to load. And so by increasing the number of qubits, you can essentially expedite and decrease that time frame. So there's practical aspects such as that allow you to do that. So we believe that it was primarily because IBM had a governor that if we built our own libraries, our own quantum libraries from scratch, we would be able to do more, and we were. But also what we found is we experimented with different types of quantum computers. So we built a quantum computer that was based off of black hole mechanics, for example, right? We built another one that was based off of cosmic rays. And we found that our cosmic ray simulated quantum supercomputer was the fastest, and we were able to scale to billions of qubits primarily because of the natural embedded error correction. So quantum computers are inherently unstable because they're trying to isolate these small particles, and they have to get the particles to stand still and do what they want, right? Like what you could imagine, could be difficult. And so you need error correction in order to stabilize those qubits. And with our cosmic ray supercomputer, what we found is that the Earth's atmosphere has a natural way, essentially filtering rays that come through, right, the Earth's atmosphere, in order to ensure that what the Earth wants and what's not harmful is what essentially passes through. So essentially, it's stabilizing in a sort of way these cosmic rays to make the most utility out of them. And so with our cosmic ray supercomputer, essentially the error correction rate is phenomenal, right? Which allows us to be able to scale to these large dimensions where other supercomputers like our black hole supercomputer or the one based off of melanin mechanics didn't have that inherent error correction attached to it. So essentially we have to look at systems in nature and look at which systems in nature have these naturally embedded error correcting dynamics and mechanics. And so in order to optimize computation, that's the realm that we've gone. We've gone away, thinking about, how can we create the next wafer, right? That's going to take computation forward. Rather, we've been looking at how can we look at systems that are already performing at high levels in nature, right? Like we built a computer programming language based off of neutrino mechanics called illuminz. So it's the infinite interplanetary language neutrino. And so
I have to pause you there a bit. I did not get most of it. So, I'm very basic in quantum computer, and I'm sure many people who are listening are as well. So when you mentioned that, a quantum computer has about 28 qubits, what I know about quantum computer is the fastest supercomputer that we have right now, if it has to solve a very complex problem, it might take about 10,000 years to solve it, right? And a quantum computer can solve it in 6 minutes. That's a huge difference. That's as far as I know, and many people know that's how fast quantum computer is. How are you matching it with nature? That's what very important is. What is quantum computer built of? How does it take photons? And how does nature come into place? Like, Earth's atmosphere and cosmic rays. How does that work in quantum computer? Because in my mind, quantum computer is just another computer, but a much faster thing. It may be built of different materials. So we have to go to basics a bit.
Okay, so let's think about what computation is at the most basic level, right? At the most basic level, you're trying to automate a human thought process, right? You're trying to create a artificial brain. That's essentially what a computer is, right? And so inherently, a computer is mimicking a biological process, but it's not doing it in the most efficient way because all of our biological processes or the building blocks of our biology are not bytes, right? They're not two-dimensional. And so
I want to say there, for everyone. So how computers mimic humans is that, maybe our hard disk, is the gray cells that human has. and
Yep.
the memory system, and at the same time RAM is our central nervous system, which runs quite fast to exchange information. That's how we emulate the human mind, and many other things like CPU and everything is there. Am I correct there? That's
Yes.
how we started mimicking the human system. Yeah.
Yep. But also there's other processes that classical computers are just not very good at mimicking, and certain processes aren't good or great. They can't be described in a good way, any other way outside of quantum. And the example I would give you is, suppose that you're getting ready to call your loved one, right? And then your phone rings and they actually end up calling you, right?
Mm-hmm.
That interaction, that was a real interaction that scientists, governments have measured, right? This non intangible interaction, this thought process, and that's working at the quantum level, right? Another example would be if you're sitting at a stoplight and there's a person next to you in another vehicle, and you can just feel them watching you. You don't know for sure if they're looking at you, but some way, right?
Yeah.
So then you look, and then you guys connect and meet. That is a quantum process, right?
Intuition.
And so essentially,
That's
yes, intuition.
We call it as intuition, and where
Yes.
waves and vibrations come into effect, because a human emits vibrations and waves, and that's how we connect.
Yes. So essentially, it is working on the frequency and the vibratory level. You could go into cymatics. You could go into, we've studied cynogenetics as well. And that's why quantum is a great technology that's already used in areas like medicine, for example, in order to simulate different drugs and the reactions that different cells might have in order or genes might have to a particular drug, right? So you can just simulate these biological and natural processes in a much more efficient way. The other aspect is concepts like a quantum teleportation, which is basically like sending information into a black hole and it coming out another black hole on the other side. Black hole mechanics isn't anything that is easy at all to simulate on a classical computer. And so, but within black holes, there are scientists that even believe that potentially other races that may be more evolved than humans may use black holes as supercomputers, right, etc. And so just really looking at some of these far out scientific theories and thought processes that do have an impact on industry. There's really no other way to test a lot of these and to put them into commerce quickly than to utilize a technology like quantum, where you could take a theory from academia, you could simulate it and test it, and then if it fits and you're right enough times, then you can hurry up and put that rapidly into production without spending a lot of money, right? And so that's all.
And how quantum enables this, because it's so fast, and it, as you mentioned, the time moves faster when we are using quantum, because 10,000 years for a supercomputer to calculate something and 6 minutes for a quantum computer. So which means that effects of quantum would be that we'll be able to move time much faster. We'll be able to move into simulating human, many human organs, and we'll be able to see what exactly is going in them. Just for example, you mentioned MRIs. We can move much deeper because computation has become much faster, and there are lots of things just like that where we can model a human into a quantum, right?
Yes. The other aspect of that is there's a lot of biological processes that occur that are sub microsecond, right?
Mm-hmm.
Like they happen within the sub microsecond time frame. And so it would just be like, for example, if we were taking a picture and we only had so many frames per second, right? Then there would be a lot of action that we would miss and a lot of insights that we would miss. And what quantum does is it allows you to speed up those frames per second substantially so that you can see processes with more granularity, and ultimately decision makers can make better decisions because they have more information than they ever had before.
So the world is gonna change a lot as we're gonna building hybrid quantum computing with AI and all. I think the implications would be that humans' lives may become much longer, and because we'll work in the field of medicine and physiology, and quantum computer can do a lot there. But at the same time, we can fly to different areas in the space because our competition is becoming much faster. So that's why it's very important. And even our internet and everything would change completely. And how much time do you think, even if it comes into effect, how much time do you think would it take? 10 years or so for quantum to like completely take over?
IBM has a plan hitting 1 million qubits by 2031. Mm-hmm. And so within the next decade, by the time they get to 1 million qubits, you're likely to have machines in offices that have a couple hundred qubits, right? From that particular perspective. Also, because these large corporations and conglomerates are pushing so much into quantum computing, what they're also doing is they're making their classical offerings legacy at the same time, right? And so while everyone's really looking at the A100 or the H100, NVIDIA servers, et cetera, for building AI applications, they know that Moore's law, right, essentially limits the amount of computation that you can do on silicon. And so in order to exceed Moore's law, which is necessary to essentially usher in artificial general intelligence, which requires more computation than is available today, you have to integrate quantum computing. And the quantum standards through IEEE, the Institute for Electrical and Electronics Engineers, that created the standards for the internet, they've already created standards for quantum computing. And I'm currently the chair for the Industry Connections Group that is essentially incubating the standards for a hybrid quantum internet that will bridge us from our classical state to where we're all running pure quantum computers.
I can imagine that there would be, as things become much faster, people and countries are going to be spending a lot on quantum computers, because I believe you can break passwords as well. When your system is so fast, you can break passwords, you can hack into systems very easily. The competition is that fast.
Let me give you an example. There was, maybe within the past month, the first cold storage Bitcoin key was broken, right?
Wow.
And the company that broke it did not tell the owner how they did it, right? But they gave enough information for a person like me to know how they did it. And what they said was it took them 1 trillion tries, right,
and
to crack it.
How much time did it take for 1 trillion tries?
See, 1 trillion tries, if you have a powerful enough quantum computer, you could do that almost instantaneously, right? And so I know that they had to use a quantum computer in order to solve that problem. But those few people in the room, in the quantum room, that are knowledgeable about it, we knew that quantum essentially makes all cryptocurrency obsolete. So if you can, so for example, a person might want to pass on that cryptocurrency, that Bitcoin, down generations, right? And we're all thinking that it's going to be hack proof, is going to be safe for generations, not knowing that it's hackable now, right? And so that changes all the different dynamics about systems, privacy, protection, hacking, and, trying to defend against those capabilities. So yes, if you're going to defend against hackers, you have to transition to quantum. And another example would be the Cleveland Clinic, right? So Cleveland Clinic is, they're at the top of the list on all the hospital lists, right? And they recently were one of the first organizations to get the quantum computer from IBM. However, the only thing that I feel is holding the industry back is that, one, you don't have enough people that know about quantum mechanics. You also don't have enough people that know about artificial intelligence and quantum. And so I believe more than anything that on the AI side, that's going to push quantum, and then quantum is going to push AI even further. And when you put quantum and AI together, that's where the magic truly happens, because now you're extending the capabilities of AI beyond those two dimensions, right? And it can think in infinite dimensions. But that's where some of the apprehension from an ethics standpoint occurs when you decide, are we giving artificial intelligence too much power if we allow it to operate in a quantum system?
Yeah, but I think, ultimately that would happen because you cannot control maybe some countries or some places where people would do that, which simply means that, good guys have to move much faster than bad guys.
Absolutely.
Because you can hack banks, you can do so many things, if quantum computing and AI mash together.
So yeah, I think but like you talked about, the good guys moving at a faster pace than the bad guys, and that normally doesn't happen. Normally the bad guys move really, really fast. But yes, that is our effort as an organization, is to move faster as white hat hackers, particularly, to move faster than the bad guys. And by doing that, we mean by coming up with exotic encryption methods. For example, utilizing quantum computing that make hacking in the classical sense obsolete, right? The sensitivity of quantum computing, when you have two qubits that are transferring information, if you intercept that, right, it messes up the whole communication transfer, right? So they'll know that you tried to hack them, and you're not going to get the information on top of that. You're going to destroy the information. And so that's why you have the government, such as in the United States, they're mandating within the National Institute of Standards and Technology, they're implementing standards within the next year or so that's going to require all government agencies and government contractors to move to quantum secure cryptographic algorithms. And so that's essentially where everything's moving. So you're right. The rest of the world's going to have to move in that direction anyway. And you also have leading scientists recently that discussed that essentially whoever wins the quantum supremacy race is going to rule the future economy, primarily because they are going to power their AI systems. And if whoever has the most intelligent AI is going to have the most robust and productive economy, and quantum and AI are married together. And so yes, it's the work that we're doing, we feel like is very, very important. But in India, they're doing some unique things in India that I think are noteworthy. One, for example, is instead of qubits, they're working on a concept called Qudits. So Qudit.
Who is doing it?
India.
No,
Yes.
In India, which organization? Is it ISRO? Is it Tata?
I believe it's related to the government. I believe it's a government initiative. And so essentially what they're doing is with the qubit, a qubit is 8 dimensions. Mm-hmm. And so a qubit is not as lightweight as a qubit. It's heavier, but in some aspects you can hold more information in a qubit. And we've done our own research on it as far as like testing the speeds, comparing the execution speeds of qubits versus qubits. Qubits were slower, but we were able to pack more information into a qubit than a qubit. So India's strategy is different, right? So they want to build computers with qubits as opposed to qubits, and have an advantage as far as being able to process more information, even though their systems may not go as fast. And so you have different countries taking different tracks and different paths to try to achieve that ultimate quantum supremacy.
Yeah, I just looked up. It's Raman Research Institute. It's in India. I'm hearing the name for the first time. I'm sorry, but yeah, it's Ministry of Science and Technology. I think India is working on that. So yeah, it's a government thing. And also our space research organization is doing it. So India is doing something very interesting, and I'm happy with that. They're packing more weight than speed.
Yep.
Right? So
Exactly.
do you think speed will kill weight? Maybe later on.
I think that it would go for different purposes. So speed would be great for artificial intelligence inferencing, right? Like at the edge, for image recognition or image classification, object detection. Speed is important there, but I think things like machine learning, right, or deep learning, I believe that more data capacity would be better there. It's kind of like what Amazon's doing with their chips to try to compete with Nvidia. They have a GPU for inferencing, and then they have a GPU for machine learning, right? And they're both optimized for those different tasks. And so I would believe that the Qubit, which India is championing, would be the best scenario and have the most utility in particularly data intensive use cases like a machine learning versus in the US or maybe China using a more photonic method with light. That may be better for inferencing, right? From that method. And so I think it depends on what your use case is, and both have their pros and cons.
Right. I'm proud of that, what India is doing. But we have to secure the qubits because qubits would be faster to maybe try to make.
Yes. Yes. I mean, but we've also conducted experiments where we've been able to create hybrid qubits. So, for example, we created a qubit that starts off as a qubit and then it transforms mid-flight into a neutrino. And then when it lands at its destination or its endpoint, it turns back into a qubit. So
What's a neutrino? What's a neutrino?
So neutrinos are they're particles that are emitted from the sun, and these particles are neutral from the standpoint that billions of neutrinos are passing through you right now, and they go through the Earth. They travel at near the speed of light, and so that was our attractiveness to neutrinos, because we wanted something that could perform better than a qubit, right? Which is just, you're just looking at an atomic molecule. So if we can look at other molecules at the atomic level and compare the performance of those, that would help to create robust telecommunication systems. So we wanted to create the fastest possible telecommunication system, have the fastest possible transactions and data transfers. And we found that by mimicking the mechanics of neutrinos, which travel near the speed of light, that was the best system that we could create.
Amazing. That's something really, really big. And how does, we started emitting, nature, how we are mimicking that, and how we are taking inspiration from that and moving it into quantum. It's really, really great. What exactly is quantum computer built of? Is it lots of silver or maybe gold components? What is it built of?
So are you talking about the inner components of quantum computers?
Yeah, the hardware.
Yeah. So it's different, right? So with some of them, for example, a lot of them are using crystals, for example, in order to create different resonance, things of that nature. You have some, for example, that are finding ways to actually put qubits on silicon. So that's one of the biggest advancements as well. And then you have, like in China, where they're just using mirrors to bounce light around, but you have to have a bunch of mirrors, and it really creates this really big system. And so you have those differences and those variances. But for the most part, people are either using they're using silicon, they're using crystals, or they're using the mirror methodology. And you have some different methods in between, but those are the primary pathways that different countries have chosen that are in the leading space in quantum.
I looked at Google's quantum, and it was made of silver, and they were like, it looked like some very different machine than we have ever seen. and it was quite different. We'll show it here. It was made of silver, and there were like some gold pipes and all they were coming up, and I could not understand how it's working. Is there a way that maybe we can share a screen and we can show that maybe this is a kind of a quantum computer, and this is these pipes do this, and this is how it works?
So here we have a quantum computer. So it looks like more is going on than actually it is. So really, they're just using these different materials that can go to low temperatures, right, etc., and are also conductive. And so silver, gold, right, these things are very conductive. With the quantum computers, they're trying to be as efficient as possible and use the most conductive materials that are going to essentially make sure that there is coherence, right? Meaning that there's not a loss of energy. And so from that perspective, all you do is have these cryogenic tubes that are just cooling down, right? The core where the actual qubits are being stored and being stabilized and essentially being encoded and decoded with information. And so essentially that's, how the processes pretty much work. And here you see how China has systems where, for example, you can see the crystals, but also you can see the different mirror setup as well. So the mirror setup requires a very large space, but current quantum computers, even the ones that are cryogenic, like what IBM has, those also require a lot of space as well. And so they're really looking for ways to optimize quantum computers so that they can go from being the size of a room to being able to sit on your lap in that particular format. And we went there from the 40s when we had classical computers that filled up whole rooms to now, except with things like generative AI, for example. Generative AI allows us to solve some of these issues more quickly than we would without generative AI. And so as a result, we foresee a lot of these advancements coming a lot sooner rather than taking decades like they traditionally would for the era of true artificial intelligence.
Yeah, this looks completely different than the other one. The first one looked very different than the Chinese one. So, how normally we have seen computers right now is they all look similar. There are racks and, how they're placed and all. So, with quantum computing, there is, it's all about speed. We can build it through different variations. Maybe, that's what quantum computing is, if I can figure that out.
Yes. I mean, in the beginning, for example, like if you think about during the early days of Microsoft or Apple, they had there were many different types of computers, right? Eventually, it went off to the PC, you got the Mac, etc., that ended up going different ways. So it may not consolidate to where there's just one supreme computer architecture for quantum. It may be that there may be multiple architectures until the industry starts to consolidate and organizations and governments find out which one of those architectures ends up being the most optimal. And you may have different large corporations that create these unique architectures on purpose to try to consolidate and to create these walls, so to say, or these moats around their intellectual property. So we may see different architectures, but I would imagine over the next decade that they would consolidate to just a few.
Great. Yeah, they'll standardize it maybe. Yeah, that's really, really interesting. So we can move ahead. What are the applications of it currently available, or maybe what's being worked on? But we want to discuss what are the applications that some people are currently working on. And is it open source? Is there any open source we can build quantum computer applications? Maybe if they are applications, if I may call it.
Yes. Yeah. So I'll start with the open source, and then I'll go to different commercial applications. So from an open source standpoint, we have open source our ill neutrino language that essentially allows you to build quantum applications on top of it. So we have a compiler, we have a virtual machine, and then we also have a server. And so you can set up a server. The servers automatically connect and sync to each other. So it'll be really easy to create a distributed system. And the servers also have artificial intelligence inferencing, for example, and training embedded within that server. And so it's already set up for you to be able to scale artificial intelligence applications and make the most of the quantum mechanics that are ingrained within that particular system and network. As far as other different languages, you also could use Qiskit once again. But with Qiskit, like we discussed, you are limited to a total number of 24 qubits. With our custom language, you could extend upon that to your heart's desire. So there are no limitations. You could add libraries and you could add modules to it and really customize it to meet your organization's needs and your application's use case. As far as different commercial applications, our organization on our infinite internet layer, we have about 30 different applications that are there. Those applications range from utilizing generative AI to create automated greeting cards to utilizing the technology to automate board meetings, for example. We have technology where we have data lakes for our IoT devices or for other organizations that want something that is more secure than on classical computers. We have encryption as a service, for example, where we have algorithms that individuals and organizations can utilize in order to secure their systems. We also have an algorithm store, for example, where we have dozens of algorithms that individuals can essentially purchase in order to optimize or speed up their particular applications. And so what we've done is we even, for example, have applications for the weather, right? Or for, watching the stock markets and the crypto markets. And so what we tried to do was we tried to take applications that were experimental and then also take applications that were everyday applications that you might see and integrate quantum into those, right? So instead of just creating like a black hole simulator or something that you might normally think of quantum being used for, we were able to integrate it into everyday applications and basically just take computationally intensive parts of regular applications code base, integrate quantum algorithms, and help to optimize and speed up the application. And so you can take quantum and you can apply it to existing applications. And since you can code in Python, you can also apply that to existing code bases and optimize your existing application without changing any hardware or changing your infrastructure or architecture.
Yeah, that's what I was coming up to, but you answered it. So there are a bunch of applications that are already being made. And if we have made an application, just for example, autonomous vehicles, if there's a Tesla which is running, how does your system come into place into their own system, and how we can connect them so that it starts getting powered by quantum?
So our system, we have an API. So essentially, individuals can just make API calls to all of our different functionalities. For those that are in the know, developers in particular, our code base is about 5,000 lines of code just for our API alone. And then we have, like we talked about, all these different application layers that run on top of that API layer. And so it's really extensive what you can do, and a lot of work has already been done. So you don't have to build this whole network from scratch. We've already integrated quantum blockchain technology. We've already integrated artificial intelligence applications. We have multiple supercomputers that are connected to our network. And so you can come in, build applications collaboratively with us, access that network. We can either host applications on our network as well, or allow organizations to migrate their particular code and host it wherever they want. And so really where our job is to become the best in the world at building these automated business and industrial applications and getting to the point to where consumers don't even ask us about the technology on the back end. They're just wowed by the presentation and by the utility of the applications we provide. And eventually we hope that the technology will disappear on the back end and we don't have to talk about it, just like we wouldn't have to talk about the mechanics of the internet in order to, get a person to use it.
So if we have an application, which is a healthcare app, and we have already built it, if we connect to your APIs, what would happen? Would the speed become faster? What is it that we'll get out of connecting to the API with the existing?
You're getting speed. 2, you're gaining security. 3, you're able to access not only a quantum hybrid simulated network, but we also have a backbone of IBM computers, of actual real quantum computers that we're connected to as well. So you can access through our network, you can access the simulated layer that's already been optimized, or you can access that quantum layer and gain the security and the speed ups of that. The other aspect is that we have quantum memory, right? Like we talked about the data lakes. So we have the infrastructure to build full scale applications. Also, we have unique AI models that you can't find anywhere else in the world that can be accessed via our API, such as our AI physician, right? Where we have algorithms for breast cancer, for depression, for COVID-19, for Alzheimer's, etc. And so we also have other models like our emotion AI, where we have the largest collection of emotions in the world. We have 50 emotions and body gestures that allow you to determine essentially how a person feels in real time, right? Mm-hmm. And when you combine,
have you emulated a limbic system there with the emotions?
No. So basically, what we did was we researched body language, right? And essentially, there was a study that was done. It's a book called "How to Read a Person Like a Book." And it was created by these two individuals in the late 70s. And they were utilizing that in order to help executives gain a competitive advantage in business negotiations. So they would accompany executives, read the body language between the two executives making the deal, step out in the hallway, let the executive know essentially what the body language was saying of the other person they're trying to close the deal with. Give them that intelligence, allow them to go back into the meeting and close the deal because they have more intelligence than the other person has. So it gave them a competitive advantage in business dealings. And so we took that same technology and we trained artificial intelligence based on the research that was conducted then, and we just expounded and extended upon that research, first doing that with IBM's Watson in 2015. And we started out with maybe like 5 or 10 emotions. And then at that point in time, we felt that the project was too important to just keep it online. And so that's when we became partners with NVIDIA and started building our own models locally on GPUs as opposed to using other individuals' clouds.
Amazing. So you have a model where if we put like 10 different people, it can read, the AI can read with the power of quantum computing, what they are thinking or what maybe they are going through right now with the gestures, their body language, their eyes, and their facial features, essentially.
Exactly. Yes, exactly. And I'll send you some demos. Like one of the demos that we did was we took old video of world leaders, right? Like John F. Kennedy, Nelson Mandela, etc. And we just have our AI algorithm analyzing them during their speeches. And you can just see all their emotional expressions when they hit certain points where they're talking favorably about the crowd or situation. You can see like love coming out of them. There's some individuals you could tell they're clearly tired, like somebody was rubbing his eyes and, it was telling he was sleepy, different things like that. So you gain a lot of verifiable context from any imagery or video that you're looking at, and it makes it more objective and measurable, as opposed to two witnesses can see the same thing. With my legal background, this is what one of the things that came out of law. 2 witnesses can look at the same crime and see different things, right?
Right.
but the AI provides some ground truth, right, and some level of objectivity, so that we can at least speak the same language and be on the same page whenever we are making important decisions, like whether this person is guilty or innocent, right, or whether we should make this business investment.
Great. Do you have access to the video right now? If we can like play the video with John F. Kennedy and all, maybe.
Sure. Yeah. Let me. So this is the first time that we actually took the technology out of the lab and took it into the public. And I had on the glasses that I had on were kind of the AR glasses were kind of large, so I kind of looked kind of strange. So if you see some people looking at me, interesting, that's what it is.
It showed common cold.
Yes, that's when we started doing our research with diseases.
Mm-hmm. So the technology can tell that if a person has a cold, that's with COVID as well. It may have helped.
Yep. Yeah, we did clinical trials with our COVID algorithm.
There's one thing that it shows lots of emotions like overwhelm, common cold, boredom, delight. A person cannot have all those emotions together. Yeah, how is it working?
I disagree. You're not showing. What we found with our research is that you don't display one emotion at once. If we had the terminal running, you would see clusters of different emotions because we're not in one state, right? Like we're constantly a ball of different emotions, and that's what we've found our research.
That's interesting.
Yep. So you'll see the emotions clustered, right? Like a depressed with a worried, or with a tired, etc. So you'll see them clustered.
Right. And were 50 emotions built by this time?
Yeah, we already had the 50 emotions and body gestures built, and this was the second version where we started to integrate the diseases, and then we separated the two models, and where we created an AI model that was just pure emotion, and that's with emotion and body gestures, that's Providence, and then with our AI physician, that's when we integrated the different diseases. But we also have AI models where we took all of our research over the past decade and put them into one AI, but we found that it works better to segment some of them out. But the emotion, and with our AI physician, it has the emotions and it has the diseases. And so for us, from our experience, that's helpful because it provides context for healthcare providers. Right? Like, right. It matters how this person is feeling. Am I making them feel worse? Am I making them feel better? And then having some type of objectivity helps with things like malpractice, things of that nature. And also combining that with the ability to make a an inference or a diagnosis, right? That also, putting those two together definitely enhances the capabilities of what can be done. But this is very early. We just recently created a partnership with S Robotica out of El Salvador, and they're one of the best companies as far as robotics in the Southern Hemisphere. And so we're working with them in order to endow their robots with our AI physician and with this technology. And so it's something that we've been careful about doing, just taking this technology and just throwing it on a robot. But we are now getting more comfortable with the technology from the last decade of research, where we feel this could provide a lot of assistance to individuals that are isolated socially, for example, individuals that need caretaking, and then also to help with staffing shortages in hospitals or medical centers where an individual could easily be screened for early diagnosis and triaged into other pipelines of imaging or caretaking.
That was very interesting. I also feel we may have something where we can do a bigger research with this, so people can move in, or we can have cameras already in place in different areas in a city. Just for example, in Los Angeles, and we can see which areas has the most happiest people and which area has the most sad people or depressed people.
You're right, because it makes sense for city planning.
Yeah, it makes sense for city planning, and where people are more depressed, they have to do something there. They have to know if there is a boundary in an area, and if people are very depressed, and if people are happy near parks, they would want to do something with that. It would give much more intelligence to town planning, and people can have much happier things.
But think about employers in office spaces, right? The return to work thing, everybody wants to get them back. But how do you make sure that your space is being utilized the most? Like, what if you have a space where you make people meet, but everyone's unhappy in that space, right? Like, it doesn't have windows, or it doesn't have the proper lighting. There aren't any plants in the room, things of that nature. And so I see it from an architectural design perspective being something that could be utilized, but even integrated into the framework of buildings and spaces. I took an architectural class it was an online class, like a free class through Harvard. And basically it talked about architectural design. And I thought how you could integrate emotion into the infrastructure of a building in order to potentially change the infrastructure. So for example, you could have a room that maybe shapeshifts, right? Like if you have kids in the room, or if a person's depressed, right? Like there's certain things that could happen, like maybe your pinball machine comes out of the wall, right? Like if you're depressed, or the music comes on, or the shades go back and let the sun in, your bath water starts. So there's a lot of ways that we can connect our emotion AI. And this is what we started to do, to connect our emotion AI to generative AI, and then also to networks like we have now, where we could control a home using technologies like a Z-Wave, right? Technology, which is a competitor to the Zigbee. So IoT technologies to extend the utility of different environments, and also the utility of other machines that are working alongside humans that need that context of how their human partner is feeling.
Amazing. Yeah, in our office space, we have used lots of yellow, so that there is
yes, absolutely.
Lots of yellow. Maybe you cannot see it, but there are plants,
Yep.
and there's like lots of yellow.
Yes. Yep. So lots of lighting. No, that's awesome. So you're doing the right thing. You're doing the right thing.
Yeah, because we're designers as well and engineers as well, so we completely understand that people become delighted when they see yellow color, because people like sun. So it ultimately emulates that. Amazing. Any other application you want to discuss, that if there is any other application that is there?
So that's interesting. One of the things that we're working on now that intrigues me is we're working on creating an algorithm to solve all algorithms, right?
Mm-hmm.
So really creating a computer that can really go beyond the limits computation. There's a lot of mathematical problems and a lot of theoretical issues that are being dealt with. And there are tough algorithms that computers, that classical computers and even hybrid computers still have some difficulties with. And so we're looking at really pushing the envelope as far as quantum computing and really looking at the most efficient way possible for a computer to solve a problem in the fastest time possible, and then take that application to other sectors and industries.
Amazing. So a computer can solve, lots of coding and algorithm problems. And how does it look for developers, for the engineers right now?
You have to become a child again, right? When you're dealing with quantum. So if you already know Python, that's half the battle, right? Because most of the quantum libraries are in Python. Okay. And so at least you're speaking the same, vernacular, so to say. But when you talk about the actual physics of quantum, and it is a different vocabulary that you have to add, right, to your existing vernacular. And so it's just a different language that you have to learn to speak. And then once you become fluent in that language, then it's a lot easier for you to develop and for you to build, because you understand the dynamics of how you operate quantum systems and what the limitations of those systems are, or where the strengths of those systems are best played.
That's amazing. Yeah. So Ian, this has been an amazing podcast. This has been an eye-opener, and it's going really deep into, what exactly a quantum computer is, because not many people know. And I hope we can continue this conversation later on, maybe in the series, where we can really see, what is happening, we can see the applications and all those things, and we can see them in effect, how they are working.
Yeah. So thank you. And if any organizations globally want to get involved in creating the next generation of the internet, which is a hybrid quantum internet, they can reach out to IEEE and their industry connections group for a hybrid quantum inspired internet. And we'd be more than happy to have them join our group.
Yeah, we'll put the links here. We'll put everything here. And, the world is open for you. Right. Thank you. Ian.
Thank you.
It has been a pleasure. Thank you very much.
All right. Thank you. I appreciate it.